So I am building off of Marguerite's discussions in the past about OU. Okay, but so I'm going to go back over the model a little bit and then go work on possible extensions. Okay, and again, if you have questions, stop, ask. Right? I mean, this is the whole thing's about you folks. So if you're not getting it, that's a problem. We want to fix it. Okay, so definitely stop me. All right, so calculating likelihood. Right, we talked about this yesterday, and here's a normal distribution. Right, if you know math is how you calculate the likelihood for a given value for the normal distribution. Right, you have the mean, you have the variance, you have the mean again, and you have your traits, your trait, your particular value. Right, if you use an R, it's just this function, d norm. Right, just basic, straightforward. We know how to do that. Right, you just plug and chug. Okay. For a tree, it's very similar. Rather than having this simple equation here, we replace, this with the variance covariance matrix and this mu with a vector of means. Okay, but otherwise, same thing. Right, to deal with matrix, inversion and things like that. But basically, it's the same formula. Okay, pretty simple. And so if you think about it, what you have is a variance covariance matrix and a mean vector. Okay, and those go into this equation. Okay, and so in all the OU models we're dealing with, all the BM models, and various other models, all we're doing is doing different variance covariance matrices, and sometimes doing different mean vectors, right? And then plugging and chugging in this formula. That's it. Okay, and so you can think about what we're doing as transformations of these, right? So, for example, if we want to have a faster rate of evolution on the blue part, I could just take those that are on the blue branch and make them longer, right? That's a way of just making a faster rate. Okay. For OU, you have to change that, and it also changes the means a little bit, right? Because being pulled towards some values. But that's all it is at heart. Okay. Trying to think about a general model, try thinking about, in what ways can a continuous character change in an instant of time? Okay. And so it could change randomly, right? Increase or decrease slightly by chance, or it could go directionally and be pulled towards some value. Okay. And so to put that into math speak, right? And so change in an instant of time, dxt, right? Which Marguerite's been showing and other people have been showing you, right? Increase or decrease slightly due to chance. So this Wiener process, right? Brownian motion, this little wiggling, right? Think of this as containing this little toddler in a box or something, or jumping bean in a box, right? And and so it's just a normal distribution, right? And we want to scale that. So we have this sigma, this rate of wiggle, to help scale that parameter, right? So bigger sigma, that same box bouncing gets magnified, smaller gets damped. Okay? So that's our rate of wiggle. Okay? Now this some value, we call that value theta. Right? So we can pull towards that theta. Okay? And here's where we are right now, right? And so if we do this thing, it would move us the entire distance in one time step. Right? Which seems unrealistic. And when I get over there, boom, I'm there. So you have to scale it in some way. And so alpha, so that's the entire difference, right? And alpha scales that. Okay? And so the smaller the alpha, the more steps it takes us, the more time it takes us to get there. Right? Yeah.
So is alpha, should I be using a microphone on the internet?
Yeah, probably.
Yeah, that's a good idea.
So theta is sort of where the adaptive peak is in trait space, and alpha is equivalent to the strength of selection, more sort of thing?
Yeah, but it's not like S and pop gen, right? It's more
Right.
complex. And Steve's going to get into that more tomorrow, right? Yeah. So,
Omega's part of alpha.
Okay.
as Marguerite said earlier, it depends, sort of the strength depends on how far you are from the optimum and stuff like that. But it's sort of a scaling term. Yep. And again, as Yusuf talked about yesterday, you can use it as to get phylogenetic half-life, right? How long does it take you to get there? Okay? And so, yeah, please.
So usually I find it useful to think about when you're far from the optimum, it's just like directional stuff. As you get close, then it becomes more like stabilized.
Yep. And so we call that the Ornstein-Uhlenbeck process, right? So we're talking about the whole course, but it's pretty basic, right? Being pulled towards something, you have some wiggle. Okay, and the analogy I like to use is, this might be an American thing only, but have you ever seen those, those toddlers on a leash sort of thing, right? Um, and so they're wiggling around a lot, right? And so the rate of wiggle is sigma. So if you give the toddler more sugar, sigma goes up, right? If the parent moves, theta, where they're being pulled to, changes, right? And if you attach more rubber bands, then that's alpha changing, okay? So that's what this process is. Okay, so now you can use it in your real life too, okay? And that's the process we're trying to model, okay? And that's still not general enough, right? Because you can imagine, before we had just those same rates over the tree, right? All the parameters are the same over the tree. You can imagine, as Marguerite said, you could paint different regimes on, right? So I could have, in this little red part of the tree, I have sigma 1, alpha 1, and theta 1, right? And in the blue part of the tree, I have 2, 2, 2, and 3, 3, 3, and so forth, right? You could go nuts with that, okay? But you can imagine then this general model where we have many of these rates, and they all can vary. You can also restrict that in various ways, right? We could say we have many different sigmas, but one alpha across the whole tree, right? Or two thetas, but one constant alpha. And so all the different restrictions all have different names and they're published at different times, right? Because we're thinking about the general model, right? And so here are sigma, alpha, and theta again. And so single rate Brownian motion, right, has sigma all equal, right? So expected variance is just time times that rate, right? And so that's constant across the whole tree. Alpha is effectively 0, right? You're not being pulled towards anything with Brownian motion, just wiggling freely, okay? And so theta doesn't matter, right? There's no pull towards anything. Doesn't really the kid has no leash. Doesn't matter where the parents are, right? It can go anywhere it wants to. And that's super simple model, right? But also tremendously useful, right? So with the central limit theorem, a whole bunch of random factors, I think Joe talked about this at one point, a whole bunch of random factors adding together, you get this Brownian motion, right? And we know that this matches a lot of, this matches genetic drift, also matches motion of the mean, of the optimum, and various other processes all map to Brownian motion, okay? Even in OU, if you switch theta enough, should map to be a Brownian motion process, right? So it's super powerful even though it's simple, okay? Multiple mean Ornstein-Uhlenbeck, right? So we have one theta over the tree, one alpha over the tree, and some different thetas, right? So Ouch does this, right? We have the different regimes for, lizards that are on an island by themselves or or share islands, right? Surface does this. The original Hanson model does this, okay? Where you keep this constant and this constant, you estimate them, but you have some different thetas, okay? Multiple rate Brownian motion. This is my claim to fame. I went from having one rate parameter to 2, yay, right? And so you have sigma varying over the tree, right? And so you imagine post-KT, the rate of mammal evolution go up, right? You can model that by having a different sigma after the KT than before the KT, right? That sort of thing. It's used in Brownie, so Thomas et al. Developed it. Medusa does the same model, okay? And then multiple everything, right? This model that, could be crazy, right? I mean, if you start fitting multiple regimes per edge, you don't have enough data, right? So you can go really nuts. But if you're careful, you can have some of these vary, some of these vary, and some of these vary, right? And so Aoi does that, Bayou can do that, okay? Any questions about that? Yeah?
This is all trait means, right?
What?
This is always dealing with trait means. Do any of them take into account, assuming you can get good population level measurements in the trait variance as well? You
can do that in, one way you can do it is by having, variance at the tips, right? And so, by default, these methods assume you measure everything precisely, right? And of course, we know that's not true. And so what that looks like, let's go back here. You are like 40 slides in, it's great. All right. What that looks like is adding something to these diagonal elements, right? So you evolve on the tree, and you have a little bit of burst of evolution or variation caused by that measurement error. And so you can put that in as a constant known term. You can put it in as different values for different species. You can, in theory, estimate it. It may not always work well. That's one way of dealing with it.
But what if you were interested in the evolution? I think this is the question.
Mhm.
Could you
You could,
do Brownian motion of trait
of the variance itself. I mean, so you,
trait becomes a variance?
yes, so you could model that trait on the tree.
So
But, yeah, go ahead.
there's a paper by Rory Rolfs that looks at this, where she implemented the variance actually evolves by an OU process, and it's a nice paper and it's worth
Cool.
looking at. But I don't think it's been applied widely at all.
Yeah. Is it an R?
No, I
Well,
think
that's
it's
why.
mostly
No.
just the yeah, exactly.
Just joking. Yeah. Okay, cool. So we're here, right? So now let's focus on this model a little bit. Okay, and so there's many ways of calling different models, and so we have these, simple names. So BM1 is Brownian motion with just one rate over the tree. Okay, basic Brownian motion. BMS has multiple rates. Okay, and S because you could have it changing based on state, right? So if you're a trunk crown anole, you could have one rate. If you're a trunk ground anole, you could have a different rate. Okay. OU, you could have one theta over the entire tree. You could have theta just different thetas varying, right? Like the ouch model. You could have theta, the mean, and A, the alpha parameter, changing, right? Different parts of the tree. You can have the mean and sigma, the variance, changing, right? The rate of or you could have all three of them changing. Okay. I mean, here's definitely like the danger zone, right? Start playing Kenny Loggins. You have so many parameters, right? But in some cases, it can be useful. Okay. So here's an example, right? So we're looking at monocots, right? And we're looking at different clades, and we think that woodiness matters in terms of genome size. Okay. And so we're trying to fit various models with this. Okay. And here are estimates, right? So the smooth plots are the empirical distributions, right? And then the colored plots behind are the estimated optimum for woody or herbaceous, and then the confidence interval, right? You notice for green, it's pretty narrow. For brown, it's pretty large. We'll see exactly how large in a minute. Okay. But it's worth looking at this to get a sense of like what your actual data are, and do they map to what you estimate. Right? As Margaret said, you have to keep looking and make sure everything's working right. And so here we have these models, right? So model names, the negative log likelihood, AIC value, delta AIC, right? So which model here is best? What? Everything varies, right? So OU MVA. Okay. And this isn't, I mean, everything varies everywhere on the tree. It's woody plants have one set of rates, herbaceous plants have another set of rates, right? There's only 6 OU parameters, right? There's ways to get crazier than that, right? But even so, this other model, MV, also has some significant weight, right? So this model is the best, but you also want to look and see what this model says too. Yeah.
Are those corrected for, or are those AICC?
No,
I guess-
because the AIC.
I guess is the sample size probably the same for all
They'll
of
probably
them,
be
right?
about the same, yeah.
Okay.
But it's still probably better to do AICC. So these authors need to up their game. Yeah. Okay, other questions? Yeah.
So, okay. So thinking about these models in a logical sense, so the OU-MBA means that woody and herbaceous plants have different thetas, and so different optima, and then they have different variance, and they have different strength of selection.
Right. So the rates of evolution rather than variance, but yeah, basically that. Yeah. In terms of genome size. Yeah. Okay. Good. Okay. And so, oh yeah.
I'm not used to seeing this W parameter. That's just a model fit.
No, that's Akike weight.
Okay.
Yep.
That's a way of evaluating the fit of the model.
You estimate the relative likelihood of the, no, so it's basically, you could just use AIC to rank the models, right? This just gives you the relative evidence for each model, right? And so they always sum to 1, right? But this model were way better than everything else. It would have all the weight. If we're about as good as this one, it would have 50-50. And so for model averaging, right, so rather than taking a parameter estimate from just this, ignore everything else, we can say, take the alpha from this and multiply it by 0.67, and then take the alpha from this, multiply it by 0.29, and get a model averaged estimate. Yep. Good. Other questions? This is great. Yeah.
The weight can be
No, so because the model could be fitting the data terribly, and the weights still sum to 1, right? It's more like, a posterior probability of that model being right. It's not a posterior probability, but it has that sort of feel. Yeah.
Okay. So do you average your model coefficients based on their weights?
Yes.
So your M parameter is determined mostly by your final model, but somewhat by that third to last. But the A parameter is then only from the last model.
No. So here we have
I
this
guess
one.
that-
This one still has alphas, right? But this has to be the same.
Okay.
And so that way, the alphas in the overall average model will be more similar than would be just with this model, right?
Right.
Some of the things with model averaging, you have parameters that aren't present, but they're sort of like equivalent to 0, right? And you can measure them as 0, or if it's truly not there, you can say, this parameter occurs in 76% of the weight. Out of those, then its estimate is this, but in the other models it doesn't have it.
Okay.
Yeah. Yeah.
So I just had a question about the weights.
Yeah.
They should sum to 1, right?
Mhm.
Since all the models, it's like relative
Right.
effectiveness. Why don't they sum to 1 on this?
They should. They don't?
No. I mean, it's only like 30 difference, but it's not.
It's probably a rounding error.
Okay, it's
Yeah.
just rounding error. Okay.
I hope. I can't do the math in my head at the moment, but someone else do the math and see if it's rounding error. And you also recalculate them from these directly and check us, but yeah. Other questions? Okay. So here are parameter estimates, right? So here we just didn't do the average, we just did the best model, okay? And here's our estimates for alpha for herbaceous plants and for woody plants, sigma, and theta, right? So what do you notice about this? So look at this for a second and see, something seem off here. And look at the CI as well. Yeah, that's pretty big, right? You don't want to see that. So what's happening there? Why is it doing that? Other than possibly bad coding or whatever, right? Right. Well, look at what the model parameters are for the other parameters. What do you see? I mean, that's your reason is the actually the reason, right? But why do we have that? Yeah. No, the optimum's really small, but it's okay if it's 0, so you could have it seems kind of weird genome size, but maybe that could be it. That's probably not what's causing the problem here. Actually, that's probably more of a symptom than a problem. What other parameters looks weird? Right. Exactly. You have your toddler, and the person has, your parent has this really, really weak elastic cord, right? So where are they pulling the toddler to? You have no idea. There's no pull, right? So if there's no pull, then you can't tell where theta is, right? So you have a huge uncertainty, right? Now a better model here would be having OU for herbaceous and Brownian motion for woody, right? We don't have that coded, right? All we have is OU for everything or BM for everything, right? I mean, this is effectively BM, right? But in terms of AIC, it's still being penalized for having those other parameters. And so a better thing would be to have different models for different parts of the tree, right? We don't have that coded yet. I don't know, do you have that? Okay. So even USF doesn't have it yet. That's crazy. All right. All right. Questions about that? Okay. But the good thing is this also shows why you actually want to look at your parameter values and look at the confidence, right? Because you want to make a whole thing about how Woody's being pulled to having no genomes. Wow, it's so amazing. Why don't trees need genes? That's not the case. It's actually just you have no idea, right? So this stuff matters. Okay. One thing that's also bad about this table. Actually, so Thomas Hanson taught this course a few years ago, and he kept driving home this really important point. If I were to say, I measured 15 mammals, and their mass was 12, you'd immediately say, 12 what? 12 stone, 12 grams? And here, we're not reporting the units, right? These have units. We're just too lazy to report them, right? And so it actually matters to report the units. People can interpret this stuff. And actually, we were developing a model last week, And we started using the units as well, and we found out we had been encoding something wrong. Like, oh wait, that's the wrong interpretation. And by using the units, we've caught our stupid mistake, right? And for just doing biology with this, converting it to units is useful, right? Converting alpha to half-life, how many millions of years does it take, is then interpretable, right? And the other approach, of course, is to go with, things that don't require units, like Margaret was talking about, right? But if it has units, you're not reporting them, that's bad, right? So again, these authors need help. Okay. So with any new method, you want to test it, right? And test it hard. And so here we did a whole bunch of different comparisons with different numbers of taxa and different rates and so forth. And you can see in some cases, we're doing a good job estimating parameters, right? In other cases, terribly, right? And the same sort of thing that Marguerite and her colleagues found as well, that like sometimes you can get things right, sometimes you can't, right? So it's always worth being cautious about this stuff. Okay, any questions about this so far? Okay. Yeah. No, this is something we did. We did a massive amount of simulations. So with varying number of taxa from 32 to 512, varying the tree shape in various ways. This is a way of testing the model as part of the original paper. Right. Now, in our exercise today, you'll do some of this yourself where you can simulate on your own tree using your own parameters. Right? So if you say, my tree says these are the parameters, you can re-simulate it and see if you get the same answer back or not. And that's a way of saying, how sure am I? Because if you have a tiny tree, it might give you estimates, but they're terrible. There's no way of seeing how bad they are. Right? Yeah?
What is the pectinate tree?
Oh, pectinate. So it's comb-like. So like a scarab beetle antennal club. Yeah, so right, that's pectinate. Yeah. And balanced is sort of the most opposite you can get, right? Where that's the same. Yeah. Good. Other questions? Okay. So in both our stuff we're talking about and Marguerite's stuff, we have this painting, right? We had to put these parameters on the tree and say, okay, this is this regime, that has that regime, and so forth. Well, how do you do that, right? And there's various ways to do that. So one is using a priori biological hypotheses, right? Like yesterday we were talking about the lizards on islands and is there competition or not, right? So Marguerite and her colleagues painted that on the tree, right? Another way is reconstructing a discrete trait and use that to paint continuous regimes. Right, so I can say woody herbaceous matter, right? So I'll reconstruct woody and herbaceous on the tree, and then paint, the parts that are painted brown get the woody parameters, parts that are painted green get the herbaceous parameters. Okay, now that can work. One problem with that is that any reconstruction is uncertain, right? And so you can find that stuff that should be woody is painted the wrong color, and vice versa, and that tends to make your models more similar than they would be otherwise. Right, and that's a paper by Liam Ravel pointed that out. Okay, so that's one potential problem. If your reconstructions are pretty good, though, it's not that big a deal. You can slice by taxonomy. So we could say, monocots versus other plants, right? Or Marguerite was talking about, frogs versus salamanders or amphibians. Right, use taxonomy for that. You could slice by time. Was there a burst of mammal evolution in the 10 million years after most dinosaurs went extinct? You can test that by painting that swath of 10 million years at a different rate. Right, and try that. There are other approaches too. So Ingrid Marler, this thing called surface, right? And there they have different OU thetas, right? They keep the same alpha and the same sigma. And they just try breaking up the tree. So they'll go and they'll have a tree that has one sigma, and they'll try painting this part of the tree with a different sigma, a different theta. And they'll try painting this part with a different theta, and try painting this part with a different theta, and try a whole bunch of those, and then try a whole step of collapsing them and say, okay, this part equals this part, move them back to the same one. Okay, so you have this build-up of number of regimes, and then a decrease in number of regimes. Okay, and that lets you, that lets your tree and the data drive where those regimes are. So you don't have to bring external information in, right? Now, in some ways, this feels hypothesis-free, right? Because you go in, there's some variation, tell me what it is. Oh, wow, these are big, that's interesting, right? But on the other hand, you can think about it as a way of, if you have some hypothesis you want to test, but don't want to push it into the analysis, you give it the data without any biases, right? And it tells you, oh yeah, maybe island matters, but really matters is latitude or something. So you pick it up that way. Okay, so this is doing that for theta. You can do the same thing with sigma, using this approach by Eastman et al. Right, where you try different rates of evolution on the tree. Okay, different rates of sigma on the tree. Same basic idea, different mechanism, but same basic idea of using the data in the tree to figure out where you have fast rates of evolution and where you have slow rates of evolution. Okay, and you can get a story from that. All right, are there any questions about those? Okay. So I'm picking on a paper from a dozen years ago, and Marguerite's views are more nuanced than this. My views are more nuanced than this. We don't actually fight about this, right? But something that if you read literature, you could see some possible debate here. And just as for learning, it's good to think about what does all this actually mean, right? So you interpret this literally. They're saying Brownian motion is purely neutral, right? And you don't want purely neutral models, okay? And it's a great paper by Hanson and Martins, right? Many of you are familiar with this, right? And what they do is look at covariance and different microevolutionary models and how they link to these macroevolutionary models, right? And all the ones in orange are basically Brownian motion models, right? So if you have random genetic drift, that's Brownian motion. Yep. If you have drift mutation balance, that's also Brownian motion. If you have directional selection with random drift, it can be Brownian motion. Fluctuating environment, Brownian motion. Stabilizing selection and environmental change, but motion of the optimum, that's also Brownian motion. Whereas the other ones are more like OU. Okay, and then there's like weird ones, right? And so the point here is a many-to-one mapping, right? So many different microevolutionary models map into the same macroevolutionary model. Okay, so any questions about that? Okay, Fongic half-life a little bit more. So tree height scaling, and so here's where it matters which program you use, because some programs rescale the trees to have height 1, and some keep them in original height. And so it would change the parameter value and what this means, right? So here, for this case, 8.4 million year half-life on this tree, right? So you go halfway from here to here in head length, in a certain amount of time per year, right? So here's that paper again, right? And here you can see, here are the actual empirical tip data, those dots. Here are the OU means, right? And you see they're not necessarily clustered around the mean, right? Why might that be? Right, so we say the purple ones are moving towards this value, but they're all over here. How do you explain that? There could be a lag, right? In this case, though, it's still kind of weird because you expect the lag to be from somewhere more in the middle, right? So it can be on this side. But right, so a lag would explain it. Yep. And here we see this arrow shows the average movement per million years. So it gives you a sense of how far they'd wiggle every million years based on our sigma estimate and our alpha estimates. Okay, any questions about that? Okay. And so back to, so it's slightly out of order. So back to what BM means. So if BM's genetic drift, then the parameters mean something for population genetics. You can easily go from one to the other, right? If BM describes a process that could be genetic drift or something else, it's then hard to map them, right? So you can have some interpretations where you map them to popgen, others where you can't, right? And so that's worth digging into. This is cool. This is then a process-based interpretation, right? We know the process that leads to this diversity. Here it's phenomenological, right? The means could be moving around because of something happening in the environment, or it could be just finite population size causing the means to move around. You can't tell which, right? And so depending on how you interpret these models, you get very different conclusions. Okay. Are there questions about this? Okay, so Marguerite talked, so now I'll talk about some controversies, right? So Marguerite brought this up earlier. So if we take, various models in Ouch and Owie and Geiger that are OU or BM models, as you gradually drop down alpha to be closer and closer to 0, in Owie, our program, the molecular converges on the same molecule for Brownian motion, right? Now, it won't be chosen because it has more parameters, right? But it sort of converges the same thing, whereas Ouch, it converges to a different thing, right? And so depending on the program you're using, they might converge or might not. So that's worth considering, okay? here by Ho and A, so oftentimes we have these ridges in the likelihood surface, right? Where I can change my optimum, so they call that mu, and change the ancestral state, right? And if I move this way or this way, the likelihood changes. Like, oh, I can estimate it, right? But if you move along this ridge, I can use any pair of those values along that line, and they have exactly the same likelihood. Okay? And so if you're doing a simple search, you might miss that. Okay? If you're doing a Bayesian approach, you might miss that too. If you have some sort of prior that tends to keep you around here, you know, you'd have it's sort of the posterior be sort of stretched out this way, but it would be infinite. Okay? It's worth looking at this. We'll talk about a way to look at this yourselves in your data in a minute. Identifiability can be a problem, right? So this is also from Ho and A. And if you have, you know, a tree like this where you have, you know, every regime is connected to itself, right? It's not disjoint, then you can't actually estimate all the parameters. Some of them are tied together, right? Whereas if you have it just something like this, now you can estimate, you know, the theta for black, gold, and blue, right? And so it's worth considering when you're setting up your model, if you're doing an ouch or owie type thing where you're painting your tree, is it going to be identifiable or not, right? And something like this, I could throw in, you know, billions of species, right? And just mathematically, you don't have enough data, right? But same thing if I said to you, you know, 5 equals A plus B. What's A, right? You don't know, right? There's no way you can know that. You can know if I give you B what A would be. You can know the slope between them, but you don't know what they both are. It's unidentifiable. And same thing here. Okay. Yeah.
I mean, how much is that a factor in your data and something that you can actually help, right? Like, what if that's,
Your question?
yeah.
Yeah. Then you're out of luck. Yeah. No, it's.
So finding another taxon that will,
Yeah, make this one evolve to be orange. Yeah. Yeah, no, I mean, that's problematic. We're seeing that, we're now more aware of that in lots of places in phylogenetics, right? So if you're using BIS, you look at diversification rates, and you only have one change that's in a cool state. You actually don't know if that's what caused the diversification rate difference or not. So you actually need a certain amount of heterogeneity. Back in the old days when you did like sister group comparisons, you know, you have to have at least 5 or something to do it. But now we know that sometimes you can have billions of species. If you don't have enough changes, you don't have enough data. So it's more about the number of changes than the number of taxa. And yeah, I mean, that's sad that you can't do that. Yeah, no solution though, as far as I know.
but in that case, it might be more interesting to look at within variation versus between. So, you know, you do have to sometimes look for what you can glean from things. Glean within claims. Yeah. Yeah. So there may be, that's our job, right, is to find the pearls.
Yeah. Yeah, and I mean, depending on what your question is, you can have the question other ways too, right? I mean, yeah, sometimes what I see people doing is like, oh, here's a shiny new method, let me use this, right? But it's actually not the way to go about it. The way you should go about it is like, here's my question, how can I answer my question? And you get some sort of approximate non-parametric approach that gives you the answer, cool. You know, as long as you're trying to figure out, you know, learn about biology from it. And so maybe all this stuff doesn't work, and maybe you just need to do some other sort of, you know, infinite contrast or something. That could work. Yeah, other questions? Okay. So another way of looking at rates of evolution is tree stretching, right? So, Joe, you're missing it. That's great. So here's a Stretch Armstrong doll that used to be sold. It was made of rubber. You could pull it, and that was his only claim to fame, right? So back to this. I mean, so we talked about how these, you know, all we're doing is messing around with these matrices and this matrix and this vector to calculate the likelihood, right? And so with OU, we have a certain set of transformations we can do. But you can do other transformations too and fit Brownian motion with these transformations, right? So Pegel's lambda, right? So what's the model here? It's not really a model. It's more looking at how the rates change over time, right? It's not like, you know, say there's genetic drift or anything like that. Just saying, okay, let's have the evolution evolve in a certain different way. So here we can have, you know, more change happening at the tips than internally, or all change happening at the tips, right? So it's a way of getting at how much of the variance you're getting is coming from evolutionary history versus stuff happening right at the tips, right? And so all you do here basically is stretch the tree, which changes your variance covariance matrix, and then plug and chug. Okay, that's it. Delta you can have a speed up or slow down, right? Are changes happening more early or later, right? And again, what does it mean mechanistically? Don't know. It could just be some, maybe the rate of browning, maybe the rate of which peaks move around is getting faster through time, or maybe your population sizes are getting smaller through time, right? You can still see, the rate of evolution is changing, right, by doing that sort of transformation. Okay? Kappa, you can raise each branch to a kappa value, right? And if it's set to 0, then basically making all branches the same length, all edges. And if it's set to 1, it's the original tree length. Okay? So it's sort of like punctuated equilibrium, right? We have change happening at every speciation event, but it's not quite, right? Because, so Eldredge and Gould punctuated equilibrium, thinking about, gradual evolution versus this sort of process, where at a speciation event, one species changes, one species doesn't. Right? That's their punctuation equilibrium idea. And here, that's not that. That is, at every node, both species change equally, right? And they have an idea that at each node, one species change. So it's a different model, right? But there could be an approximation of it, right? And there's other approaches, too, you can use for this. If you actually want to look at how much change happens along branches versus at speciation events, Fulmer-Bachmann has a series of models that can do that, right? So you can estimate how much change has happened along the branches versus at these nodes, okay? And one thing that makes these harder than just like transforming the tree is if you think changes happen at speciation events, you don't have all speciation events in your tree, right? You've missed a bunch of them, right? The species you haven't sampled, the stuff's gone extinct, and so you've missed those changes and sort of correct for those in theory, okay? You estimate what they are and I think iterate over them. Yeah. So questions about this? Yeah.
No, I'm still not sure on these parameters, lambda, delta, and kappa.
Yeah.
How those fit in. I'm just not
Okay. Yeah. Here, let's do one. Let's do kappa. It's easiest. Yeah. No, there's simple ways of transforming the tree, right? And so it's not based on, I think evolution works in this way. I think there's stabilizing selection or anything. It's just based on, let's have things mess the tree up in certain ways to make it speed up or slow down, right? So it's not pop gen, but it is a way of looking at rate heterogeneity through time. So if we have a tree, so let's make this branch length 2, this branch length 3, 3, 5, A, B, C, right? So my regular variance matrix is, what would it be here? So what's this element here? How much time does A share with itself on the tree? 5. Yep. Okay. How about A with B? Hold up your fingers. Give me a number. Yay, 2. Okay. C? C with A? 0. Okay. And then B with B? 5. Yep. B with C? Right. And now it's symmetric, right? So 2, 0, and 0. Yeah, I know. I'm sorry. It's dynamic. Okay, so that's our variance covariance matrix now, right? All right, now what if I do a kappa transformation, right? So let's raise this to 0.5. Right? So what would it be? So this would be 3 to the 0.5 plus 2 to the 0.5. Right? That'd be my new, and so forth.
I get it. You're scaling it in different ways using different parameters.
Yep. That's why I call it tree stretching, because you're just like moving the tree around, and that changes the variance covariance matrix. Yeah. The Brownian motion thing I did with different Brownian motion rates, what you're doing is just saying, if I have, sigma 1 here and sigma 2 here, my variance covariance matrix has, this time times sigma 1 plus this time times sigma 2. Right? And so that's another way of basically stretching this matrix and allowing you to transform it. So now you can imagine making your own transformations, right? So you want to say, do I have a faster rate that then declines through time or something? You could say, okay, let me take those branches right after the KT and have them double in length and then decrease as a function, as a, an exponential or something. That's a new model you just made. You can just transform the variance covariance matrix, plug and chug. Right? So it makes it very, very flexible. Yeah?
Well, it's kind of a comment, and it might only be helpful for me, but that's kind of equivalent to what is taught in contact dense now in terms of like walking functions with genetic similarity to make mistakes and things like that. By sort of random warping to the relationship matrix to get out. In that case, you have a known prediction accuracy you can use to verify that walking function. But it seems very similar.
Oh, cool. So I don't know anything about those, but good for them. One thing to watch out though is, you could have too many warpings here, right? So I could have like warping for this branch and this branch and this branch and this branch, and I'd have now 4 parameters and 3 data points, which is bad news. So that's why you have like, Pegel's transformations are single value and so forth. Yeah. Do you have a question? Or, okay. Oh, no. All right. Yeah.
Speaking, though, you're no longer really doing Brownian motion.
Right. Or you could be thinking you're doing Brownian motion, but your time scale is no longer time. It could be something else that changes through time.
Right.
Yeah.
Might be part of the history.
Yeah. Other questions or thoughts? Okay, only 40 slides left. Kidding. Okay. Here's another transformation you can imagine doing, right? So, basically what I'm doing here is saying I can transform the branch lengths after this time to make them smaller, or at that time to make them bigger, right? That's the same thing as saying my sigma squared after that time is 20% of the original value or double the original value, right? So it's still Brownian motion, but you can do it as a tree transformation rather than a rescaling of the sigmas, okay? You could imagine doing, 3 slices or something like that, okay? And again, it's just the same thing where you just rescale this for the branch lengths and create a new model. Okay, other questions about this? Okay. And of course, the OU thing we did before is effectively changing the branch lengths, right? So information decays over time, plus changing the vector of expectations, right? So Brownian motion, the expected value is always what you were at the mean, right? You just randomly walk. With OU, it's a mixture of that, what you started with, and where you're going to, right? As Margaret showed, you're 26% this way and 74% this other way, right? Same set those things. So you're just transforming that vector too. And that's how we put this all in the same framework. All right, so all pretty straightforward once you get that. Questions about that? Okay. So that's cool. So what can we do with all this stuff, right? And one thing we can deal with is heterogeneity, right? So for example, we can have heterogeneity by state, right? So here we look at rates of evolution of, actually this is molecular evolution rates, of trees and shrubs versus herbs. And we look and find, that these evolve more slowly, right? Which sort of makes sense when you think about it, because they have much longer generation times, right? And so they may have fewer mutations per year. And so they evolve at a slower rate. And so you look at, if you wanted to fit this with continuous data, you just take the tree and try stretching it to have the woody things have a smaller branches, right? And we can try dealing with heterogeneity this way, right? So do we think that whales are evolving the same way as shrews are? Probably not, right? In terms of body mass or anything. And so we can try fitting different models to whales versus shrews, right? Through painting regimes or through transforming the trees. Okay, so there's all sort of ways of dealing with character evolution.